Hello students, and welcome to the pre-lab video for uniform circular motion. Well, you've seen cases of uniform circular motion before. So here I have an object rotating uniformly in a circle, and there is a force. You've learned in lab there must be a net external for the path. We call the force a centripetal force. Well, we're going to consider a device today in lab that will allow us to measure a value for a magnitude for the centripetal force for an object undergoing uniform circular motion. So this is the setup, and students struggle a little bit using this setup correctly, so I hope you pay attention to the hints I give you today. Typically it will come fairly well disassembled like this, so I want to show you the essential parts and how to put it together. So there is a central post, and it is mounted in a very low friction bearing down here, and you will see it will allow the apparatus to rotate uniformly for a long period of time. There's an arm like this, and it goes through the upper part, and it only goes in one particular way, so I'm going to put it in here. I'm doing it the wrong way, so I'm going to do it like this. You'll see on one side you have a little set of ears and a little rope right there, and that's where you hang the mass that will undergo uniform circular motion. So I'll hang it there like this. So you will need the distance from the point, the center of the rotation, to where the mass is. That will be the radius of the circle, and you will need the mass, the value for the mass of the hanger here. Often you'll find it is written on the mass already. So I would hang that there like this, and then there is a spring that goes from the mass to this central hook here, and we will attach that like so, and you'll see the purpose for that in a minute. Now, there's a counterbalance that must go on the rod at the top here, or it will not rotate in a very nice way. It will wobble and tip over on you. So now we have that part fully set up. Some of the other features of the uniform circular motion setup. So there are 3 adjustable legs down here on the bottom, and you'll want to take a torpedo level and adjust the legs so that it is level in both dimensions, this way and front and back that way. You will adjust them like that. You also want to have the setup already towards the edge of the table. You'll notice there's a pulley on this side, and you'll see the reason for that in a minute here. So the idea is, as we rotate, there will be a force that will tend to elongate the spring like that, and the magnitude of that force will be equal to the magnitude of the force of centripetal acceleration, the centripetal force. And we want to get the force so that it exactly pulls out the spring to the point where there is a 90-degree angle between the vertical of the mass hanging down and the spring. So you have a little post here on the apparatus that's mounted to the bottom, and it's adjustable, and I can move it back and forth this way, and it's there for you to use as a guide. So what you want to do is initially bring the mass out so that you have this 90-degree angle here, and then set this little device here so that it's right below the little pointed mass. And you'll use that as a guide later to make sure you have this 90-degree situation. So, as I said earlier, you would measure the distance between here and here. That would be your radius. And then when you put it into motion, you'll want the speed around the circular path to be so that it pulls it out so that it's at this 90-degree position. Now, I could set it in motion like this, and you notice it will continue to rotate like this for a long time, but the speed isn't enough to pull it out to the 90-degree position. Okay, so I could do a little more here, get it going a little faster, and it's pretty obvious I'm going beyond the 90-degree mark. So the trick is to get the speed where you're right at 90 degrees between the spring and the hanging mass, and that's right about there. So then I would take a stopwatch, I would start it, and I would measure the time for, say, 10 complete revolutions. then if I divided that by 10, I would have the time for one period, the time to go around one time. With the radius and the period, I can compute the speed of the mass around the circular path. And with the mass, I can then compute the centripetal acceleration. So that's how you would determine the centripetal acceleration. Now, we can repeat the same setup, get another value, and maybe you would do it 2 or 3 times. But you might also increase the radius by loosening this screw here and pushing this rod out a little further. In this case, we have to stretch the spring further to reach 90 degrees. We'll have to rotate it at a different speed. We'll get a different centripetal force, but we can repeat the experiment again. I get it rotating so that we have about a 90-degree angle there, and it will rotate like this for a long time. It's a very low friction bearing there. So again, I might measure the time for 10 periods, determine the period for one revolution. Then with the radius and the mass, I can compute the centripetal force. So I might again change this distance up here and repeat it again several more times and have, say, 3 different centripetal forces for 3 different radii here of orbit. Well, we can determine the centripetal force another way, and we'll use this for our known value. Determining the centripetal force while rotating the device, we call that the dynamic method. We call this other way the static method, and we'll use that as a known value. Well, we have this pulley here. What is it used for? Well, what if I were to just take a hanging mass like this, and I were to hang it across the pulley, and you'll notice you can attach it. There's a place where it can be attached on this side of the mass right there. So I can hang my weight hanger right there, my mass hanger, and I can add mass until I pull the hanging mass out to a 90-degree angle. So let's see, is that about it? That's about it. I need a little bit more here. And when I get it in that position, I say, hey, then the weight on the hanger is equal to the centripetal force for this particular radius. So I can use that as a known value for the 3 different cases where I just used the dynamic approach to get the centripetal force. So the static method for determining the centripetal force, and then the dynamic method I just demonstrated. Please review the video if you need to. Students do struggle with this setup a little bit, but it's a pretty neat way to measure the centripetal force and verify the equations we've developed in class for uniform circular motion. So you should have good luck with this thing, and I look forward to seeing you in the lab.